Okay, can you hear me? Yes. So it's going to be on gravitational waves. And I have to say the title is a bit misleading. It's not really about making the waves, but more on how we detect them. So as an introduction, I'm quite sure you all know that last year the LIGO and Virgo collaboration have announced the first detection of a binary black hole, stellar mass binary black hole merger. And this discovery has been made by observing the gravitational waves that has been emitted by during the merger. So I'm going to, it's going to be the main subject, gravitational waves, black hole. But before talking, I want to explain you that, and the funny thing is that last year it was the centennial anniversary of gravitational wave, the first publication of Einstein, and I want to spend some time on the different developments, experimental developments that, in some sense, lead to the discovery of in LIGO data. Then I will mention, so I will briefly describe the source of gravitational waves and explain you how we do this, how we search in the data the gravitational waves. So I will actually insist on the binary system case and mention briefly the other searches we are doing. And of course, I will go through different the outcome of this discovery. So a little bit of history. 1915, so this is the first paper of Einstein about general relativity. And the next year, he published another paper where he mentioned, so I tried to find the original paper in German. I'm not speaking German, but it's funny to go back to these original papers. And so he mentioned gravitational waves in this original paper about which is dealing with the integration of the equation of gravitation. And what he's mentioning in this paper is that, so he's trying to estimate the amount of energy that the system, the amplitude of the wave. And what he's saying here is that typically the emission of waves must have practically vanishing value. So he was not really taking gravitational waves very seriously, or at least he was not believing that this is something that can be detected at that time. And so there was another paper 2 years after about gravitational waves, where he derived more or less all the things that we are still using, like the quadrupole formula, where all the things we use at the first order to describe gravitational waves is in this paper. Then, of course, you know, the same years, in 1960, there was a paper by Schwarzschild describing the solution of the equation of Einstein. The word black hole was not mentioned at that time. It was just a solution of the Einstein equation. This solution was named black hole, or at least the object behind this solution, the metric, was called black hole much later. And one thing, so that's the most important papers about gravitational waves, but during many years, actually, until the 50s, people were wondering if those waves are real or if they are just artifacts of the theory. And even Einstein was not really a believer at the beginning. And in 1936, he was trying with Rosen, he was trying to publish a paper. He published a paper where he said that the gravitational waves do not exist. But at the same time, people were, someone like Robertson, who was the referee of the paper, initial version of the paper that Einstein was trying to submit in PhD, was saying, no, actually, this is not true. Gravitational waves are real. But it took really a long time for the community to realize that they are indeed real. They are not an artifact of the theory. And there's a really important, so That means that between 1916 and the 50s, there was no real experimental attempts to try to detect gravitational waves and discuss about possible sources and things like that. So an important, really important moment in the domain was what happened at the 1957 conference, the third GR conference in Chapel Hill in US, where you had the conference was about the quantization of general relativity. But there was all the most important people of GR at that time, and especially Pirani. There was not only Pirani, you had also the most important theoretician. And at that conference, so a year before, actually, Pirani had published a paper on the physical significance of the Riemann tensor, where actually what he did in this paper is to show that the relative acceleration of two particles is associated with the Riemann tensor. And the derivation is quite simple, is that if you take two particles that are free-falling, that means that they will follow geodesics. So here you have the geodesic equation. And you will consider, two particles following two geodesics separated by a vector xi, a small distance. And so you have the geodesic equation for the two particles moving on their geodesics. If you do the difference, and you do a little bit of calculation, you obtain this formula, which is the geodesic deviation equation that relates the vector xi, the second derivative of the vector xi to the Riemann tensor. And so it makes a link between the geometrical properties of the space-time and the acceleration of particles. And if you consider, so I will come later, because if you derive and if you express the non-zero component of the Riemann tensor, behind that you have actually the gravitational waves here. But another important thing, so this is what explained in the 1956 paper of Pirani. And this has been discussed during the conference quite a lot. By the way, if you look at the proceedings that are available online, the proceedings of this conference are very interesting because you have the questions and answer report, and you see all the great people of that time, the questions they were asking and the answers. So it's really a very interesting source of information, the proceeding of this conference. And at that conference, what I wanted to add, is that Feynman was present. Feynman was not really a big fan of GR, or at least was not really working, Feynman is Feynman. And so he was participating to the conference, and at the end, he made a presentation where he came back to Pirani's presentation and tried to explain by hands what it means. I mean, what the geodesic deviation equation means by hand. And this is a famous sticky bed arguments. And this is really the argument that convince people that gravitational waves are real and can be detected. And the argument is the following. You take a rod, a stick, which is rigid, and you have two particles, two beds, that can move freely on the road. When you have gravitational waves going through, what the gravitational waves will do is to move one particle on the road. And if the particle, if the bed is moving, that means there is friction on the road, and there must be energy deposition on the road. And so it's a thought experiment, but this is, and actually behind that, this is exactly what the detection principle we're using with laser interferometer detectors, is we are trying to measure the distance between two particles that are free to move. So what we are doing is trying to measure the change of distance. So this is something, so I wanted to mention that because historically, this conference played a big role for the experimental aspect of gravitational waves. And at that, yeah, I will come back because at that conference there was Joe Weber. And Joe Weber was a young physicist, experimental physicist. And he was present at that conference. And when he came back to this lab, he started to think about how to design a detector to detect those gravitational waves. So I will come back to that later. First of all, let's try to finish the derivation of what we can do with geodesic deviation equation. So if you if you simplify the problem, taking the two particles, one at the origin of a local Lorentz frame and one at a distance of L. So if you see which are the non-zero Riemann components, there are a few, you can, which are related to the metric tensor H. And so the equation becomes simply, if you simplify the problem, this equation, which is the second time derivative oxy is proportional to the distance between the two particles and the second derivative of the metric tensor. So you just need to integrate twice, and you obtain this famous formula that tells that the difference between between the 2 points, the relative distance, change of distance between 2 points, is proportional to the metric perturbation. And that means that h being the amplitude of the metric perturbation, h being the gravitational waves. And this is what we are using. So I want to show you how actually, I was mentioning so far gravitational waves, but I didn't tell you where it comes from. And actually, so it comes from the Einstein equation. It's a solution of the Einstein equation in vacuum. If you're far from, so what we are assuming here is that we are far away from the source. So we are in a vacuum, and we will linearize the metric. So what we will consider is a flat metric, the Minkowski metric, plus a perturbation, which is the gravitational waves. And if you try to solve the Einstein equation, you will obtain this equation that becomes, in absence of matter, so you suppress the energy momentum tensor, you obtain this equation, and a simple solution of this equation is a plane wave. And you can show that you can impose actually several conditions, especially the transverse and traceless gauge, and you can show that there is only, so the solution has only two independent components, which are the two polarization of gravitational waves. So you have the gravitational waves have two polarization that are just plane waves that travels through space-time. So don't forget, so we are always considering in that case that we are far away from the source. We are not, when we detect the wave, we are very far away from the source. So what are gravitational waves? It's just, as I was mentioning, it is just a deformation of the metric. So we are in flat space-time, and we have a small deformation due to the acceleration, due to a source of gravitational waves. I'm going to mention that later. But the gravitational waves is propagating through the flat metric, and it's just a deformation of the metric. The point is that, and this is what Einstein realized it in the initial paper, is that space-time is very rigid. I mean, to distort space-time, you need to have very violent source. I mean, you can't, if you try to generate gravitational waves on Earth, you can. I mean, you take a huge, a compact body, a piece of metal, you rotate it at very, very high speed, the maximum. What you will obtain is you can emit some gravitational waves, but they are really, really weak. I mean, not detectable, even with the LIGO Virgo detectors. So that's why we are looking for sources that are generated by super compact objects. I mean, black holes and neutron stars. A relativistic object. I mean, they need to move very fast because you need to have. You need to have relativistic object and very energetic. So typically the sources are astrophysical. But the good thing is that the amplitude of the gravitational waves decrease with the distance and not with distance square like an electromagnetic wave. So we gain with that. So as I was mentioning, the gravitational waves have two polarization, which effect will to, so you have a wave that propagate and that will deform the metric, or more exactly, the metric deformation is a wave. And if you have two, I mean, the effect of one polarization will be to stretch the distance in one direction and at the same time shrink the distance in the perpendicular direction. And the other polarization is doing actually the same, but with a rotation of 45 degrees. So this is, and this effect on the gravitational waves on matter is the principle of the detection that we are using to detect them. So one source which is very important, and actually it's another date which is very important in the history of the experimental detection attempts, is the discovery of the binary pulsar, the first binary pulsar discovery in 1974. So it has been observed by Russell and Joe Taylor. What they observed is one pulsar, and then they realized quickly that there was something weird with the timing they were receiving from the pulse. And the basic conclusion was that the pulsar they were observing was this pulsar that was emitting some electromagnetic waves, was disturbed by another object they could not see electromagnetically. So it's very important. Why it's very important is that because it's an example of compact object with in rotation, meaning with non-spherical geometry. That means that it will emit some gravitational waves. Because I forgot a slide that tells you that actually the quadruple formula of Einstein, that shows that the amount of energy emitted by a source is proportional to the second derivative of the inertial moment. So you need to have an inertial moment that is not symmetrical, that varies with time. Otherwise, you have no emission. So you need to emit some gravitational waves, you need to have some asymmetry of your source. And a binary system is something which is asymmetric, not non-spherical symmetric. So this is Joe Taylor and Russell, and they got the Nobel Prize for the discovery of the first binary pulsar. But immediately, people realize that this is a perfect system to study gravitation. And this system should emit gravitational waves. And in 92, so this pulsar has been observed now since the 70s, so for more than 40 years. And in 92, the first publication by Joe Taylor and Joel Weisberg showed something people were expecting. So that curve that we always that is shown to prove that gravitational waves exist is the following. That shows actually, as function of time, the time shift between the time shift of the periangstrom. That means that it shows the decay of the orbital period. That means the system is losing energy through gravitational waves. It emits some gravitational waves, so it's losing energy. That means the orbital period is increasing. And so the curve shows the prediction given by general relativity, and the points are the measurement. So that was the first, in 92, the first experimental proof or indirect proof of the existence of gravitational waves. Of course, here in this prediction, what is assumed is that all the energy loss of the system is due to the emission of gravitational waves. And this seems to be the case. So this is the latest measurement of this very nice object. So over 40 years of measurement, you see the prediction by GR, and you see the data points. So Joy Weisberg is still continuing with his students to measure this pulsar. So let's come back to the first experimental attempt. So I was telling you at Chapel Hill conference, there was Joe Weber, seen here with his first detector. And he was really excited by trying to detect those gravitational waves. So his idea was that a gravitational wave which is arriving on Earth should, if you have some piece of metal, it should excite the resonance, the mechanical resonance of a big bar of metal. So he started to build such kind of detectors called bar detectors, just a piece of metal was surrounded by some actuators, and the mechanical excitation is transferred to some at the end and converted into an electrical signal. So he built several of these detectors at different points and made his own data taking, analyzing all by himself his data. And in the 60s and 70s, actually, he claimed, at least there is one paper published in 1961 where he claimed to have observed some coincidence between two bars. So he claimed to have seen some gravitational wave events. And actually, if you read the paper, you would realize quickly that it was just noise. I mean, what he was observing was just noise in his detector. I mean, the understanding of the noise of those detectors, people realized that it was, the environment of those detectors are very, very important. At the same time, the people were starting to publish a first paper on possible sources of gravitational waves. So it came rather late, the first publication, about possible, estimation of the amplitude of astrophysical sources that could be detectable on Earth. You see the frequency range is around the Earth. So roughly at the same time than Joe Weber bars, there was an attempt to, there was people clearly realized, so to detect gravitational waves, what you have to do is to be able to measure precisely a change of distance between 2 points. And to do that, if you take just a standard scale, you're not going to be able, remember the order of magnitude of the amplitude is 10 to the minus 21, as I was mentioning earlier. So if you just take a scale, you're not going to have the precision to measure such kind of change of distance. So you really need to have a detector, an apparatus that is very accurate. And one device which is very adapted for that is laser interferometric or interferometers. At At that time, laser was invented. That's another key point in the domain, because without laser, we could not do such kind of experiment. You need a very stable source of light in your interferometer to be able to measure accurately a change of distance of the order of 10 to the minus 18 meter. So it's really a challenge. So there was, as always, there was some Russian guys in the 60s that proposed to use laser interferometric detectors to measure the change of distance due to gravitational waves on Earth. But the first one who tried to design such kind of device was Forward, a student of Joe Weber in 70s. And in 70s, he built actually the first prototype. So the first laser interferometer prototype, it was a tabletop experiment, few meters interferometer. But this is the first prototype. And you see the design, so it was very simple. So what you see is actually Michelson interferometer in vacuum with opticals that are suspended. People realize, so you need to have free falling masses point. So you need to suspend to isolate your mirrors from any movement. So it was the beginning, the very beginning of these detectors. And I was mentioning the point is that you need to measure, to be able to measure the change of distance of the order of 10 to the minus 18 the change of distance 10 to the minus 21 in h. So I want to show you how it works. So I need to switch. Yes. So this is a laser. So it's a simplified Michelson interferometer, or simplified LIGO detectors, I would say, where you have a laser going through. So here you have the beam splitter mirror that splits the laser beam in two. So you have two arms, and here so the two beams recombine here, and you have your photodiode here where you detect some fringes. And when you have gravitational wave passing through your detectors, what it will do is to shrink the distance in one. So it will shrink one arm, while in the other arms will be the length will be increased. And if that means that you have a change, your light phase will be changed, and you should observe when you have no gravitational waves, you should be on the fringe, and when a gravitational wave is passing through, it will change the phase of the light, and you should see some change in your detected light. So this is a basic principle of the detection. So the idea of laser interferometers came in the 60s, I was mentioning, but in 72, another important date, Revis, a physicist at MIT, made a very thorough analysis of all the possible noise that can impeach the measurement. And so he went through all possible noise, coming from noise of the laser, the frequency, the phase, the amplitude noise, the mechanical thermal noise of the antenna. Each piece, the mirrors will, so the mirrors are at room temperature, so they will be moving because of the thermal noise of the atoms. There will be noise induced by the laser on the mirrors. There will be, of course, seismic noise of the ground, external noise of the environment. For instance, the magnetic noise of the environment is something very important because it can couple in the detector. So this actually was this study is very important because it was the first time someone was able to prove that not only you can build a detector, but it can measure something. Because, people always come with, regularly you have someone proposing a new apparatus to detect gravitational waves. But most of the time, people forget to, if you really want to prove that your detector is able to detect, you need to prove that you can control all the noise. You can see the signal above the noise. So that's why this study is very important, because it was really convincing people. Because then, so people started to have experiments like that in labs. So it's a prototype at MIT. So this one is few meters. So it's small scale interferometer. But so in the 70s, 80s, people started to build several prototypes, not only in the US, but also in Europe, especially in Germany, at Garching. Garching group made lots of very nice experiments where people were actually improving the device, not only considering a simple Michelson interferometer, but adding more stuff to improve the sensitivity of the detectors to be able to detect gravitational waves. So the technology in the 70s, 80s improved quite a lot. And in the end, you had a proposal. So at that time, it was no more prototypes, but of few meters interferometers. But it was the big detectors on Earth to really detect gravitational waves. So there has been two proposals, one in US, funded by NSF, proposed by Reva, Skip Thorne, and Driver, these three guys. So they made this proposal, so it was in 92. So it got accepted by NFS. It took a while, of course, because what I forgot to mention is that, as I said, it's no more prototype tabletop experiment. It's kilometer scale interferometers. Here you have Virgo. So in Europe, the equivalent of LIGO is called Virgo. You see a picture of the experiment in close to Pise. So in Europe, you have Alain Briet in France and Giasotto in Italy, who joined and proposed at that time it was French and Italian project. Now it's a European project. So a little bit of word about the spectrum of gravitational waves. So actually it's very wide. I mean, the spectrum goes from hertz, from the Earth, up to very low frequency, 10 to the minus 16, where you expect gravitational waves, where this is the domain of the primordial gravitational waves emitted during inflation. So this is something we expect to see one day, especially in the CMB, but not only in the CMB, but that would be CMB experiment, if they see something in the polarization one day, that would be a wonderful thing. But with other detectors, we are trying also to detect those primordial gravitational waves. I'm not going to talk about them today. I will concentrate more on what is accessible on Earth, with LIGO Virgo detectors, and it's above the 1 hertz. So, and there are projects in LISA, the LISA detector that will hopefully be launched in 15 years. It should be able to cover this range of gravitational waves, millihertz, and with pulsar timing, you can go even lower in frequency. So the whole spectrum, which is expected to be emitted by different sources from, primordial gravitational waves up to stellar mass, black hole, or core collapse supernova. But here you have the range of the supermassive black hole merger, which should be accessible by this experiment. So the spectrum is very wide. So a little bit of word about a few words about the sources, and especially the one, actually, so the one that we are trying to detect with LIGO Virgo detectors. So they are classified, so as already mentioned, actually, the binary coalescence system composed of black holes or neutron stars. So in that case, we know quite well the waveforms, and we will use them. And the duration of the signal is quite short, from few seconds up to few minutes, not more. The other source, another source that was considered a long time ago, are the gravitational waves emitted when you have a heavy star. In the end of its life, the core will not be able to sustain the the gravity, and the core should collapse, and that should emit some gravitational waves. So during this collapse, those sources are quite short normally. I mean, when the core collapses, it takes less than 1 second. The point with those sources is that the waveforms are not very well known. I mean, some simulations are available, but they cannot, I mean, they are not really, I mean, it's so difficult to simulate one collapse that we can't use completely the waveform as we do for the binary system. So another source of gravitational waves is the one emitted by isolated neutron star or neutron star in binary system. If they have a little bit of cross deformation of the, I mean, at surface of a neutron star, you can have a little bit of deformation, and we expect that this deformation will be big enough to such that some gravitational waves, the system emits gravitational waves. In that case, the source is continuous, and it's well known. It's just a sinusoid, so it's quite, I mean, the waveforms is known. The point is that you don't know the parameters of the source, so it's not so easy. And finally, if you take all the sources that have been emitted from the beginning of the universe, I mean, primordial and astrophysical sources, they have emitted gravitational waves. So in the end, all these gravitational waves should add up, and that will form a stochastic background of gravitational waves. So this is something we are looking for. And for each type of source, so this is a simplified list of sources, because we have other type of sources that we are looking for. But this, I would say, category of sources, for each category of sources, I was telling you when, for instance, when the waveform is known, when the waveform is not really known. And for each type of sources, the techniques will be different. For instance, when you know perfectly the waveform, you will use what we call match filtering techniques to extract the signal from the data. When you don't know, and this is the case as well for the isolated pulsars. When you don't know anything about the source, the waveform, like for instance the stochastic background, what you will do is just correlation. The only thing you know is that if you have 2 detectors, that's another issue, you need at least 2 detectors, that you should observe exactly the same signal in the 2 detectors. Modulus of effects due to the fact that your detectors are not located at the same time. So it's another type of technique called correlation. First, what you will use, you don't know exactly the waveform, but what you will use is that the fact that the signal is short. So it should be continuous in time and frequency. So you're going to search for an excess of energy in time frequency space. So it's just an introduction to searches, just to tell you that for each type of source, there is a technique which is different. And that makes, of course, things a bit more complicated. So compact binary sources, coalescence. So let's spend some time on that. So as I was telling you, you have a binary system, form of neutron star or black holes, or black hole and neutron star. They will coalesce for many, many years. until, so they are losing energy. So they are losing, they are emitting gravitational waves. So they will, the two objects will come closer and closer, but it will take millions of years, actually. In the end, it will merge. The two objects will be so close that they will merge. And what we observe, so for many years, so you have binary system exist. We observe, now we have many observations of, for instance, binary neutron star. So we know that they exist. We know that they are losing energy. And the point is that it takes, all the system, for instance, that we observe, the 1 hour, the Olsen-Taylor pulsar, we know that it will merge in, I don't remember, in millions of years, not tomorrow. But we can expect that from time to time, we have one that will merge. Because the only thing, what I forgot to mention, and this is where what you see here, is that the amplitude, so the amplitude is increasing. The closer you are from the merger, the higher the amplitude is. So what we are able to detect is only the end just before the merger. So the end of the coalescence, where the two objects are still separated, and the merger, where you have lots of energy which is emitted. So this is what that's why what we observe is the merger, not the beginning. LISA will be able to observe for many years one single event, but not LIGO Virgo, because actually when it enters, I will tell you why. We observe, the point is that it's the frequency range of the detection. So another source was mentioned in core collapse supernova. So what's very important with this source is that gravitational waves will allow to understand better what's happening during the collapse. Because those objects, supernova, are observed, but only with electromagnetic emission, and this is something that is emitted way after the collapse. So gravitational wave is really the probe that will tell you what's happening at the beginning of the collapse. So this is one of the reasons we want to observe such kind of object, to really do some astrophysics with those objects. There are other kind of burst sources that we are looking for, like, for instance, cosmic strings. This is a source which not astrophysical sources, but they are expected to emit gravitational waves in the frequency range of LIGO and Virgo detectors. There are lots of things. The point with core collapse supernova is that what we expect is to have one. The amount of energy that is emitted is not as big as for a binary system. And we know that with the LIGO and Virgo detectors, we cannot observe something far away. Right now, with the current version of the detectors, we cannot go beyond the galaxy. So we need to have one core collapse supernova in the galaxy. And it's quite rare. The rate of such kind of events is typically 1 per galaxy per century, something like that, or 3 per century. So it's quite rare. The last one was in 1987. So we are waiting for such kind of event in the galaxy. So even if we go, there are some models that tells that with advanced LIGO design sensitivity, we could go up to 20 megaparsec. That means go to the local group. In the nearby universe. In that case, if you were able to go to 20 megaparsec, the number of sources is increasing. We could expect something maybe, for instance, 100 per century. That means one per year. But this is very optimistic, and no one is believing that. So periodic sources, I was mentioning, it's sources emitted by neutron star that have a little bit of deformation at the surface. So the waveform is well understood. You just need to match a point. You don't know anything about the source, except for a few pulsars that we observe electromagnetically. In that case, you know the position in the sky, you know sometimes the frequency. Those sources must exist because neutron star exists. What we don't know is the amount of deformation of the neutron star. That means the amplitude of the gravitational waves they will emit, if they have enough deformation. And stochastic background, I was mentioning, it's a source of all emission since the beginning of the universe. So I'm going to spend maybe the last 15 minutes on searches. So searches has not started last year. I mean, last year it was the announcement of the first detection with LIGO in LIGO data. But actually, the searches have started. I mean, the LIGO and Virgo detectors have been funded in the 90s. The construction took about 10 years. And in the 2000, data taking started with LIGO. And what you see here is the campaign of data taking for LIGO, Virgo. Virgo is always a bit late compared to LIGO. And in between, what you see in between two data taking, there are commissioning where the detectors are improved. I mean, the problem with those detectors is that it was the first time that such detectors were built. So it took some time to build them, make them function, and reach design sensitivity. It was not really easy. So that was, I mean, the 2000, there was data taking, nothing was observed, but people learned how to use and how to make those detectors work. There was a small upgrade of those initial version of the detectors at the end of the last decades. But really, the breakthrough came with the setting and the advanced detector, where in terms of sensitivity, we gain a factor 10. So let me explain you the sensitivity of the detector. So what you see here is the noise spectral density. The noise spectral density, I should have written the formula, it's just the Fourier transform of the autocorrelation of the noise. You take your noise, your data, you autocorrelate them, and you take your Fourier transform, and you square that. And this is what you obtain as function of frequency. And what it tells you, so this is what was obtained with the first generation of detectors. What it tells you is that if you have a signal, for instance, a binary neutron star, if it's big enough, I mean, if the amplitude is big enough, you should observe something at some point here. If the signal is here, you're not going to observe anything. It's below your noise. If you want to be able to measure something, I mean, an excess of energy in your data, I will mention that, I will explain you later how we do that. What you should have is a noise which is below your signal. Otherwise, you don't see anything, you're blind. And that was a point for many years. For many years, the signal, the binary system were merging. All these years, I mean, there were some events somewhere in the universe, but they were, I mean, the sensitivity of the detectors were not low enough. And so from the first generation to the second generation of detectors, that was the goal was to go from that sensitivity curve to this one. How we could do that? So this limit, this noise, this curve was limited here by seismic noise. So here at low frequency on Earth, you're limited by seismic noise. Below a few dozens of hertz, we were limiting. So there was a huge work on the isolation of the mirrors to reduce the seismic noise to a few hertz. Now we are limited at almost here. The second part of the noise limitation was this one, and it was due to thermal noise, due to the agitation of the atoms in the mirrors. So to reduce that, we change all the mirrors. Especially the coating of the mirrors have been improved. The material has been, you need to have very low Q material to reduce the thermal noise in that frequency range. And here you're limited, the sensitivity is limited by the power of the laser. So to reduce the noise at high frequency, the kilohertz region, you need to increase the power of your laser. So this is what I was explaining here. And this is the result of last year, actually. Here you have the sensitivity curve of initial LIGO in green. And 2 years ago, 2015, when advanced LIGO started taking data, that was the noise spectrum that has been measured. And you see the gain between initial LIGO and advanced LIGO. But what you see here is that actually the design sensitivity. That means that LIGO has not yet reached the design sensitivity. So there is room for improvement. And the design sensitivity, it was foreseen. The point was not to start with the design sensitivity. The design sensitivity should be reached in 2020, around 2020, in 3 years from now. But believe me, to go from here to there, it's not easy. It was in some sense quite easy to go from here to here, there, but the last bit are not so easy to reach. So some picture of the detector. So that picture of the mirrors, I was telling you the mirrors are suspended. What you see here is only the lower level of the mirrors. So the mirrors are some blocks of silica suspended by very thin silica wires. And they are something like 100 kilograms. And they are big, 30 centimeters large. We are working in very high vacuum tubes. You have a laser, high power laser, and what is very important is that it's stabilized in frequency and amplitude. And in the end, yes, what we observe, what we measure is a signal on the photodiodes. That means some watt that are calibrated. In the end, we convert the watt into H after calibration. So what we measure is just a time series, the measurement of the photodiodes that looks like, which is just noise. And from time to time, we have a signal in this. But it's not, normally it's not visible like that, this signal. So picture of the last stage of the suspension. In that case, it's Virgo. So you see the mirrors. It's very complicated technology to be able to reach those performance. So as you know, so in 2015, LIGO went on. There was a few months data taking where the performance were quite good and very stable. That means the sensitivity was not changing a lot, was quite stable. So we took data. And since November of last year, we are again taking data. And we will stop this data taking called O2. So the first one was called observation. O is for observation, O1. And O2 is the second run. And from time to time, we have commissioning breaks to repair broken stuff or improve the sensitivity. I was mentioning, so far I mentioned Virgo and LIGO. So LIGO actually is composed of two detectors, two kilometer scale detectors in US, one in Washington and one in Florida. Virgo is in Italy. So LIGO was operational in 2015. Virgo is still under commissioning and will join O2 with LIGO by the end of this month, actually. So it will participate to the end of the O2 run. And in construction, you have a Japanese detector called Kagra in Japan. And it's still under construction, should be in commissioning next year and operational in 2020. And with a similar sensitivity to LIGO and Virgo. And there's another interferometer that has been at least funded, which is not yet under construction. It's actually a LIGO detector, but installed in India. And why we have this network of detectors is to be able to determine where is the source. Because what I didn't tell you is that those detectors, when you see something in the data, you don't know where it comes from. And to be able to localize the source, you need to have several detectors, at least 2 detectors, to be able, if you measure the time difference of the signal arrival in each detector, you can reconstruct the position in the sky. At least with 2 detectors, you know that the source is of a ring in the sky. With 3 detectors, it's going to be the intersection of the 3 rings, the different combination of 2 detectors. In that case, you have 2 points, right? And it's easy. With 3 detectors, you can localize the source, I mean, as a point in the sky with a certain precision. Another thing which is important for having a network of detectors is to be able to get rid of false alarm, because those detectors are very noisy. Tell you that they are very precise, but they are totally, what we are measuring is noise. And I mean, what we are detecting is, I mean, the noise of the detectors are not stationary, they are not Gaussian. So if you don't do coincidence or correlation between 2 detectors, you will be totally, I mean, you're not going to see a signal. And I mean, because you are going to see only background events. And I think I will stop here because it's 5, and I will continue tomorrow, and I will go into the detail of the searches.
Okay, thank you very much.